Hello, welcome to another one of our lessons in our chemistry lecture series. This topic is volumetric analysis. We will be looking at titration and its calculation during this particular topic. The objectives that will be covered in this topic will include explaining the principles involved in the different types of titrations. We have acid-base titration, we have redox titration, and we have thermometric titration. We will be carrying out calculations involving these titrations. Now, the principles are the same in terms of titration, and the calculations are also the same. The only difference is, one, in the case of acid-base titration, uses indicators, while redox and thermometric titration does not. Let us start our lesson. In volumetric analysis, it is a quantitative investigation of chemical reactions by comparing reacting volumes. Now, this is known as volumetric analysis. The procedure by which reacting volumes are determined is known as titration. What is titration? In simple terms, titration is a method of using a solution of known concentration, called a standard solution, to find the unknown concentration of another solution. We are going to look at what is a standard solution, how to make it up, and how to use it to find the concentration of the other solution. Now, in titration, the solution whose concentration is known is very important, and this is called the standard solution. This solution is normally placed in the burette, and the solution of unknown concentration is placed in the conical flask. So, in order to do or to carry out your titration, we must first make up a standard solution. Let's look again at what is a standard solution and how do we prepare a standard solution. So now, a standard solution is a solution of accurately known concentration. This simply means that if you know the concentration of a solution, it is a standard solution. Now, it can be prepared by one of two methods: measuring mass and by dilution. Now, measuring mass is simply weighing out an accurately known mass of a solute and then dissolving this mass into a volumetric flask and making it up to the mark. That is the measuring mass method in preparing a standard solution. So, let's say we want to produce a standard solution of 0.5 moles per dm cube sodium carbonate. So we know that we have sodium carbonate, and we want to produce or make up a standard solution of 0.5 moles per dm cube in a 500 cm cube volumetric flask. So how do I make up this solution? In order to make up this solution of concentration 0.5, I need to know what mass must I measure out. In order to find the mass that I must measure out, I will use the formula number of moles equal concentration times volume. Remember that your volume must always be in dm cube. So my concentration is 0.5 moles per dm cube, and my volume is 500 cm cube, which I will convert to dm cube by dividing by 1,000. If I do that, I'll get 0.5 dm cube. So dm cube would cancel dm cube. So what is my value? in terms of moles. 0.5 times 0.5 equal 0.25 moles. Now that I know the moles of sodium carbonate, I can find the mass of sodium carbonate. So, mass equal moles times molar mass of sodium carbonate. So it is 0.25 moles times the molar mass of sodium carbonate, which is 23 times 2 plus 12 plus 3 times 16. And that will equal a mass of 106 grams per mole. So mole will cancel mole. My calculation here now would be 0.25 moles times 106 grams per mole. So 0.25 times 106. That will equal to 26.5 grams. So what can I do with this 26.5 grams of sodium carbonate? Well, this is the mass of sodium carbonate that I will now transfer to a 500 cm cube volumetric flask, dissolve it in a small amount of water, ensure that all the crystals are dissolved, and then make up to the mark with distilled water. And once I have this solution, this is a concentration of 0.5 moles per dm cube sodium carbonate. And that is how we make up this standard solution, by measuring mass. So this mass is a mass that we would measure out to make up our standard solution. This solution will now be used in titration to find the unknown concentration of another solution. So I can use this concentration to find the concentration of, for example, an acid. Let's look at the other method, which is dilution. Now, the dilution method is done by calculating a known volume of a more concentrated solution, which is then diluted to give the volume of a solution of the required concentration. So let's say that we have a bottle of concentrated hydrochloric acid. For you to use that acid in the lab, the concentration of, say, 8 moles per dm cube would be too high for you. The concentration would be too high. That would be very dangerous. So we must get this down to a lower concentration, that in the event some of that acid spills, then you will not be harmed. So let's look at how we will calculate the volume that we would need to take from that concentrated bottle to put it in a volumetric flask and make up to the mark to get a less concentrated solution of that hydrochloric acid. Let's begin. So we know that our concentrated HCl is equal to 8 moles per dm cube, 8 molar, very concentrated. Now we want a much lower concentration. For example, we want a concentration of, say, 0.01 moles per dm cube HCl. And we want this in a 500 cm cube volumetric flask. We are going to use the dilution method in terms of the calculation. So we'll use C1 V1 equals C2 V2, where C1 is your initial concentration, V1 your initial volume, or the volume we will need to measure out from this 8 mole per dm cube solution to put into the 500 cm cube volumetric flask and make up to the mark to get a concentration of 0.1 moles per dm cube. So we know C1 to be equal to 8 moles per dm cube. We know V1, that is our unknown. So we know that is the unknown. We know that C2 is the concentration that we want of 0.01 moles per dm cube. And we know volume 2 to be 500 cm cube. Now in this case, there's no need to do the conversion of cm cube to dm cube because the units would cancel out in the equation here. So we need V1. So we are going to transpose this equation. So from that, V1 is equal to C2 V2 over C1. And that will give us C2 would be 0.01 moles per dm cube. Always work with your units. Times V2, which is 500 cm cube, divided by C1, which is 8 moles per dm cube. We see here that the units would cancel out in terms of moles per dm cube with moles per dm cube. So our volume will be in cm cube. So what is the answer here? Let's check. 0.01 times 500 is equal to 5 divided by 8. And that will give us a volume of 0.625. Now this is a very small volume to measure. But let's say that we could measure this volume accurately. If this is the volume that we get from the calculation, in order to get this concentration of 0.1 moles per dm cube HCl, I would then need to measure this volume and place it into a 500 cm cube volumetric flask. So this volume will be placed in this volumetric flask, dissolved in water, it's aqueous already, and then make up to the mark and ensure that the meniscus is sitting on the line. And this will now be an accurately known concentration of HCl, that is 0.01 moles per dm cube HCl. And this is how we make up standard solution by dilution. We can now go into the different types of titration now that we know how to make up a standard solution. So if I'm doing an acid-base titration, I would need to make up a standard solution. If I'm doing a redox titration, I would need to make up a standard solution, and the same thing for a thermometric titration. Now, as we go through this topic, important terms that you will encounter: equivalence point, end point, indicator, oxidation and reduction, which forms redox, exothermic as well as endothermic, titrant and titrand. Now, as we go through and we meet upon these terms, we will explain them. Let's go. Now, a titrant is the reagent of known concentration. In other words, your titrant is your standard solution. And we said earlier that the standard solution is normally placed in the burette. So the titrant is coming from the burette and it will be placed into the conical flask when it's run out, and that is called the analyte. So the titrant is running out into the analyte or titrand, and that is found in the conical flask. Now, when you run your titrations, especially if it's acid base, remember that there is no color of the acid. The acid is colorless, the base or the alkaline is colorless. So we need to use a particular solution to identify when we should stop running the acid into the base or the base into the acid. And so we use an indicator. Now the indicator is the solution that we use to tell us when to stop the titration. The indicator indicates the point at which the reaction has ended. Now we have different types of indicators. Let's look at a few. We use litmus paper. Now litmus, its color in acid is red. So if you have blue litmus, in acid solution, blue litmus should turn to red. If you have red litmus and it is placed in alkaline solution, then the red litmus should turn blue. So here we have our color change. Phenolphthalein, which is colorless, if it is placed in acidic solution, it should remain colorless. But the moment that that solution becomes alkaline or basic, it changes to pink. Methyl orange is another popular indicator. And methyl orange in acidic solution is pink or red. But the moment that that solution becomes alkaline, it changes to yellow. And so we use this principle to tell us in an acid-base titration when the solution move from one acidic or alkaline to alkaline or acidic. If the solution is acidic and we run the titrant into the solution, it should remain colorless if we're using phenolphthalein. But the moment that we run the alkaline solution from the titrant and the conical flask which contain the acidic solution, the moment that that becomes alkaline, then the color will change to pink, and it is saying to us that stop running the titrant into the analyte because I am now finished. I reach what is called the neutralization point. And we call that point the equivalence point. Now, the equivalence point is not noticeable by the naked eye. So, what do we look for? We look for the end point. The end point is a point at which a color change is observed. You will not observe a color change at the equivalence point, but you'll observe a color change at the end point because that is the point at which the solution is either slightly acidic or slightly alkaline. Let's look at a titration diagram to explain this point. Now, if we're doing an acid-base titration, we are going to determine the concentration of an acid or a base by neutralizing the acid or base with another acid or base of known concentration. So here we have our burette, here we have our pipette, and this is our flask. Now, let's say that we are finding the concentration of an acid. If we are finding the concentration of the acid, then the base, being sodium hydroxide, will be our standard solution. Now, both the acid and the base, they are colorless. But here you see some color, so you can see the difference in the movement of the liquid as we change volumes. So think about it when doing your titration. The acid or the base is colorless. And that is why we need an indicator to give us a color change to tell us when to stop running the acid or the base, depending on what is in the conical flask and what is in the burette. So if I have my acid here, it is colorless. The first thing we must do is to put in our indicator. Now let's say we are using phenolphthalein. If I drop phenolphthalein in this flask, where the solution is acidic, then it should remain colorless. Why? phenolphthalein is colorless in acidic solution. The moment I start dropping my base from my burette, the solution will continue to be colorless. Now, if I'm dropping base, let us use OH to represent base. And let's say we have, these are drops of alkaline solution. And we have acid solution in our flask. Now, every drop of alkaline or sodium hydroxide from my burette into my flask would cancel or neutralize an acid. So the solution inside the flask here is still predominantly acidic. I drop another drop of base into the flask. That base would neutralize another acid. It is still colorless because I am still acidic, shown here by the H plus ions. I drop another one, neutralize another acid. I have one H plus left, so I am still colorless in terms of my indicator because I am still acidic. The moment I drop another base and into my flask, this is saying now that my acid is completely neutralized. Now, this is the point at which we call the equivalence point. The equivalence point is the point at which the concentration of the OH minus ions is equal to the concentration of the H plus ions. Now, at this point, there is no change in my solution. The color is still colorless. Now, when will it become pink? If I drop another OH minus ion from my burette into my flask, there are no more H plus ions to react with that OH minus ion to neutralize it. So I will now have OH ion being the predominant ion, which is alkaline. So what was in my flask is no longer acidic, but now alkaline due to the presence of this OH minus ion. So the color now would change from being colorless to pink. This is called now the end point, the point at which a color change is observed. And I would now stop running my solution from my burette and I would take down that value. So, what would I do with that value? That value we would put in a table, and that table would consist of my titration and titration 1, titration 2, titration 3. Now, we need volumes. Now, notice that the pipette that we use is a 20 ml pipette. And we use that 20 ml pipette to measure out 20 ml of acid and place that acid into the flask. Now, we are going to run the sodium hydroxide from the burette. Now, let's say we start at 0. So our initial reading is going to be 0. So here we'll have initial volume. And whatever you put in a table is coming from the burette. So my initial volume is 0.00. When I run my alkaline sodium hydroxide into the acid, let us say I get a volume of 20.01. That is my final volume. So my initial volume was 0. And I run from initial to final. And let's say now this is my final reading. And that volume is 20.01. The volume of sodium hydroxide used would be now equal to 20.01. So initial is 0. The final is 20.01. The volume of sodium hydroxide used to neutralize this particular volume of acid is 20.01 cm cube. So we're going to have our unit in the table here. And so there's no need to put units in this section of the table. So now that I reached 20 cm cube, I could continue running because the length of my burette is 50 cm cube. So if I run 20, I can run another 20 without finishing the solution from the burette. So our initial reading will now be 20.01. Now let's run our volume from 20, which should now be our new initial volume, and run, and let us say we run and reach a volume of 40.01. Now the volume used would now be 20.00. So my first titration, which is my rough titration, which tells me where the volume would most likely be, is 20.01. My second titration is now 20.00. Now I have about 10 cm cube of sodium hydroxide left in the burette. So I would now need to top up, but there's no need to top up to 0. So let's go to 10. So we'll top up to about a volume of 10 cm cube. So our initial reading will be 10. Now we run the volume from 10 and we get a volume of 30.01. So my volume used now, when I subtract my 10 from my 30, would be 20.01. Now I have my 3 volumes used. I must show the volumes that I am going to use in the calculation. So I will tick this volume and this volume that are either the same or they are within plus or minus 0.1. Now if I use all 3, they would be within this particular range. But since I have 2 volumes that are very accurate, I will use these 2 volumes. So the average volume used, average volume of NaOH is equal to 20.01 plus 20.01 divided by 2. So my volume that I will use in my calculation would now be 20.01 cm cube. So this is really saying to me that it took 20.01 cm cube of sodium hydroxide to completely neutralize 20 cm cube of an acid. And let's call this acid HCl. So now we can carry out our calculation using the standard solution, which we would know this concentration and its volume, to find the concentration of an unknown HCl. So in doing our calculation, we can work out mass concentration as well as molar concentration. So here we say that we have different ways of stating concentration in chemistry. Either your molar concentration, where the unit is moles per dm cube, or your mass concentration, where the unit is in grams per dm cube. Let's look at molar concentration. Now your molar concentration is the amount of moles of a substance present in 1 dm cube of solution. Hence, molar concentration is moles per dm cube or moles per volume. So here we have the unit mole over the unit dm cube. Hence, moles per dm cube for our molar concentration. Now, in looking at our calculation, here we see where they're asking us to find the molar concentration for a solution containing 80 grams of sodium hydroxide in 1 dm cube of solution. Now, if they had asked for the mass concentration, we would simply divide this mass by 1 dm cube to get grams per dm cube. But they want the molar concentration, so they want moles. So the first thing we're going to do, since they want molar concentration, is to convert mass to moles. To convert mass to moles, we need the molar mass of sodium hydroxide, which we know already is 40. 23 plus 16 plus 1. So we say moles equal mass over molar mass. And the mass is 80 grams divided by the molar mass of sodium hydroxide. So 80 divided by 40 grams per mole. Now this would be equal to 2 moles. So now I know that I have 2 moles of sodium hydroxide. I can now find my molar concentration. Now we'd use now the formula moles equal concentration times volume. And remember that our volume is in dm cube. So I need concentration, which is the molar concentration. So we're going to transpose to make that the subject of the formula. So molar concentration is equal to moles over volume in dm cube. So the moles is 2 moles over my volume of 1 dm cube. So my molar concentration here is equal to 2 moles per dm cube. And that's my molar concentration. Let's look at some others. Now, suppose I want to find the mass concentration instead of the molar concentration. Now, I would not need to convert mass to moles because we want mass concentration. So we would simply say mass concentration is equal to mass over volume, which is equal to 5 grams over, and the volume is going to be converted to dm cube, 0.5 dm cube. And so 5 divided by 0.5 is equal to 10 grams per dm cube. So that is my mass concentration. So you'll notice here that in order to find mass concentration, I need the mass and I need the volume to give me grams per dm cube. But suppose we were not given the mass. Suppose we were given molar concentration to find the mass concentration. What would we do then? Let's check. In this case, they're asking for the mass concentration, but this time we're given molar concentration. And we know that we're looking at sodium carbonate solution. So we have the molar concentration, which is equal to 0.5 moles per dm cube. And we know that we're looking at sodium carbonate. So that's Na2CO3. Now remember that we must write the correct formula or else our calculations will be incorrect. So since we know that, let us use the relationship mass concentration is equal to molar concentration times molar mass. And we can check this to ensure that it is correct, because grams per dm cube must be equal back to grams per dm cube. So for molar conc, it is moles per dm cube, and for molar mass, it is grams per mole. So you see where mole cancel mole, so my unit is still grams per dm cube. So the relationship that we will use to calculate mass concentration whenever we're given molar concentration is mass conc equal molar concentration times molar mass. Now we have our molar concentration of 0.5 moles per dm cube. And we'll multiply that by the molar mass of sodium carbonate solution. So the molar mass of sodium carbonate is 106 grams per mole. And so mole will cancel mole. And so we'll now multiply 0.5 by 106. So 0.5 times 106 is equal to 53 grams per dm cube. So what is the mass concentration of 0.5 mole per dm cube sodium carbonate? Well, the mass concentration of 0.5 moles per dm cube sodium carbonate solution is 53 grams per dm cube. Now, here is a very good titration question. Now, it's saying that 25 cm cube of 0.02 moles per dm cube sulfuric acid neutralizes 18.6 cm cube of sodium hydroxide solution. Find the concentration of sodium hydroxide solution in moles per dm cube, as well as finding the concentration of sodium hydroxide in grams per dm cube. So they're simply asking us to find the molar concentration and the mass concentration. Now there are some simple steps to follow. The first thing we must do is to write an equation and establish mole ratio. Let's do that. So sodium hydroxide plus sulfuric acid will produce a salt, sodium sulfate, plus water. Put in our state symbols: liquid, aqueous, aqueous, aqueous. Then we balance. Here we have 2 sodium, but here we have 1, so we put 2 here. 1 sulfur, 1 sulfur. Well, let's balance this as a polyatomic ion, so call it 1 sulfate. 1 sulfate. So we're okay with sulfate ions here. Water consists of 2 hydrogen. So we have 2 here and 2 here, that's 4. So I need 4 in totals on the right hand side. So I need to put 2 here. Now I have 4 hydrogen here, 2 oxygen here, and 2 oxygen here, because we already accounted for the sulfate ions, which consist the oxygen here. So we're balanced here. Now the mole ratio between sulfuric acid and sodium hydroxide here, based on my equation, it would be 2 to 1. So the first thing that we're going to do is to identify which solution is a standard solution, and then calculate the moles from that standard solution. So if you look at this, we see where we have 0.02 moles of sulfuric acid. So that is the standard solution. So step 2 then would be to do the calculation of the standard solution. So moles of sulfuric acid equals concentration times volume. And the concentration here is 0.02 moles per dm cube. And that is times 25 cm cube, which is 0.025 dm cube when I divide 25 by 1,000. Now multiplying 0.02 by 0.025, that should give me a mole of 0.0005 moles. Let's check. 0.02 times 0.025. That equals 0.0005, which is 5 times 10 to the minus 4. 1, 2, 3, 4. So this is the moles of sulfuric acid. So the moles of sulfuric acid can be used to find the moles of sodium hydroxide. So from this, I could say that the mole ratio between sodium hydroxide and sulfuric acid is 2 to 1. So NaOH to H2SO4 is 2 to 1. So we're seeing then that we know the moles of sulfuric acid, so the moles of sodium hydroxide is twice that mole. So 2 times 0.005 should give me a value of 0.001 mole. So mole of sodium hydroxide is equal to 2 times 0.0005, which is equal to 0.001 moles. So we now know the moles of sodium hydroxide. So our next step, after using the mole ratio to find the moles of sodium hydroxide, is to find the concentration of sodium hydroxide, knowing that I now have the mole of sodium hydroxide and the volume. So here we can say now moles is equal to concentration times volume. But we know the moles of sodium hydroxide now to be 0.001, and we know the volume to be 18.6 cm cube, which we will convert to dm cube. So we can make concentration the subject of the formula. So concentration is equal to moles over volume. And so the moles is 0.001 divided by 0.0186. And that is in dm cube. And that should give me a value of, so 0.001 divided by 0.0186. That is equal to 0.05 moles per dm cube. I now know that the molar concentration for part A is 0.05 moles per dm cube. So I can now find the mass concentration using this molar concentration and the molar mass of sodium hydroxide. So we will now say mass conc, which is the mass concentration, equal the molar concentration times molar mass. And the molar concentration is 0.05 moles per dm cube times the molar mass of 40 grams per mole. So 0.05 times 40 is equal to 2. So here, our mass concentration would be 2 grams per dm cube. So the molar concentration here is equal to 0.05 moles per dm cube, while the mass concentration is equal to 2 grams per dm cube. So if you follow these simple steps, you can calculate any titration questions. So here we have 30 cm cube of 0.1 molar sodium hydroxide. Now molar, capital M, is the same unit as moles per dm cube. So we need to determine the concentration of the acid. In this case, the sodium hydroxide is a standard solution, which we would put in the burette. So let's write down the steps so you can carry out this calculation on your own. So step 1 would be to write the equation. Step 2 would be to calculate the number of moles of the standard solution. Step 3 would be to use the mole ratio between the acid and base to find the moles of the other solution. Once we find the moles of the unknown solution, we can now go ahead and find the concentration. So let's see quickly how we could do this. In step 1, we would need to write the equation between sodium hydroxide and hydrochloric acid. So you'd write quickly NaOH plus HCl, and that would produce sodium chloride plus water. Put in your state symbol, aqueous, 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 aqueous. You would realize that this equation is already balanced. So the mole ratio between sodium hydroxide and HCl is 1:1. You would then calculate the moles of the standard solution here by multiplying concentration times volume in dm cube. When you get that mole, the mole ratio is 1:1, so the moles of this substance here is the same moles of HCl. Now that we know the moles of HCl, we can find the concentration of HCl by simply saying moles of HCl divided by the volume of 25 here. But the 25 must be converted to dm cube, and that would give us our molar concentration.